Hi, my name is Manish Gupta, and in this video, I'm going to talk about Pythia suite for analyzing large language models. So let's get started. What is the Pythia large language model suite? The motivation to create this suite of model checkpoints is to answer questions of this kind. How do large language models develop and evolve over the course of training? So when you do pre-training, what all changes in the weights, in the weights and the patterns that these large language models learn? How do these patterns change as the models scale as well? So when you are pre-training smaller models versus larger models, how do these patterns change? Right? So to answer this question, folks came up with this suite called as Pythia, which is a suite of 16 decoder-only autoregressive large language models, which are trained on the pile data set and in the exact same order. So their data loaders are exactly synchronized. Okay. They trained two kinds of models, one on the original pile data set and the other on deduplicated pile data set. Pile dataset, it's important to note that pile dataset is actually very commonly used. It has been used by several other models like GPT-J, GPT-NeoX, Jurassic 1, Megatron Turing NLG model from Microsoft, OPT model, Woodhouse model, and so on. Right. So overall, as part of the suite, they have released 16 decoder only autoregressive large language models. But then for each of those models, they have released 154 checkpoints, right, at different stages of pre-training. Uh, the model architecture is primarily the same as GPT-3, but they have also included all recent popular things like flash attention, rotary embeddings, parallelized attention, feed forward technique, and also their embedding and unembedding matrices are untied. They have trained for 300 billion tokens, so these are all rigorously trained models as such. Uh, Deduplication. So they have, of course, trained, these 8 different sizes. So 8 sizes and then deduplication versus not. So that is how there are 16 different models. And they've observed across various experiments that deduplication does not really have any clear benefit in terms of language model performance. Okay. Of course, they have released trained models, analysis code, training data, all on that link. So if you want to try out the Pythia suite, that's available there. So these are the size of models that have been put out, from 70 million all the way to 12 billion, the largest one. It starts from 6 layers and goes all the way to 36 layers. And then, a different model checkpoint that you see here are equivalent to several other GPT Neo or OPT models. OK. So if you compare it with other different, families of models which are publicly available. So if you look at GPT-2, well, they have only one checkpoint, and they have, 4 different models in that census, ranging from 124 million to 1.5 billion. If you look at T5, again, they have only one checkpoint, but then there are different sizes which are available. So T5 is small, T5 extra small, and medium and large, and so on, base and large, and so on, right? So Pythia is the only one which has like 154 checkpoints per model which are available. And there are 8 different models, as you see there, right? 8 different models. And then, you have 154 checkpoints for each of them. So that's that. And then the smallest model is 70 million all the way to 12 billion. So it's like a very nice gradation in terms of model sizes as well. GPT-3, as we know, basically there are several checkpoints. Only one of them is, only one checkpoint is publicly available though. And one checkpoint per model, and there are 4 different models. 4 different models. Okay. So now, based on this suite, what can you do, right? So essentially, what kind of analysis you can do? What kind of patterns can you discover about the evolution over the course of training for these large language models? So they do various analysis, and that is what I'm going to talk about in this video. So first analysis is about figuring out how does data bias influence the learned behaviors in LLM. So as you grow, as you pre-train this model more and more, how does the data bias change over time? Okay. So basically, you see 2 charts. This first chart, or rather, let me talk about these charts. But then before that, let me talk about the actual experiment that was done. So the idea was that they have several checkpoints: 70 million checkpoint, 410 million checkpoint, 1.4 billion checkpoint, and so on, several sizes. So they take a checkpoint, and 7% prior to the end of the training, what they do is to resume the training of the model with the bias handled. Okay, so how do they handle the bias? Well, 7% prior to the end of the training, they actually are going to further resume the training and pre-train the model in the same way as was done in the original model. They are going to use the same exact data, except that they replace the masculine pronouns by feminine pronouns. in a way to actually handle the gender bias. Okay. So therefore, what you see here is that for the last 7%, 93 to 100%, right? You will see that there are two curves, two red curves, two blue curves, two green curves, and two yellow curves also. Okay. Now, except for the green one, where this thing actually starts from 21%. So this is basically 21%. So for Pythia 1.4 billion checkpoint, they basically do 21% before the end of the training. You essentially resume the training, resume the pre-training, and then you try to the pre-training data, you replace masculine pronouns by feminine pronouns, and then you observe what happens. Okay, so that's that. So they did this observation on two data sets. One is called as the Crow's pairs data set, Crow's pairs data set, and the other is the Vino bias data set. Okay, so the first chart is for Crow's pairs data set. The second one is for Vino bias data set. Now, here on the x-axis, what you see, of course, is percentage of training data, and the same on the right side as well. On the y-axis, what you see is percentage of stereotype. So the idea is that this captures percentage of times that the perplexity of the stereotyped sentence, you can think of stereotype sentence, the bias sentence. So perplexity of that sentence is lower than its less stereotyped counterpart. Okay. Now remember, lower perplexity means better. So percentage stereotype basically means the model is biased. Okay. So higher this value, the worse it is, right? You would like to have smaller values. That's the idea. Okay. So what do you observe? You observe that as you do more and more pre-training, your stereotype percentage increases, which is basically meaning, yeah, accuracy increases for the model, the model gets better, but then at the same time, it also gets biased. So that's the first observation. The second observation is that if you do any intervention, in the sense that if you basically replace masculine pronouns by feminine pronouns, you see that, the dotted lines are always below the solid lines, which basically means that there is a decrease in stereotypical accuracy for each intervention and across model scale, right? So that's that. Now on the Vino bias data set, by the way, on the y-axis, what you have is accuracy being plotted. So what is accuracy? Accuracy basically means that, so Vino bias data set is about trying to replace a pronoun by a proper referent. So it's a co-reference resolution task such that if you do co-reference resolution accurately, then it is against the stereotypical biases. Okay. So basically the idea is that this y-axis sort of represents the proportion of the time that the probability of stereotype pronoun as an answer was higher to a multiple was higher, right? Was higher compared to the correct replacement. Okay. So again, the lower this value, the better it is. The lower the value, the less biased the model is. And what you observe, so you observe that on Pythia 6.9 billion, if you apply the intervention on this green curve, right? On this green curve, you apply the intervention, you observe that and this is the 50% line. This is the 50% flat line, right? So observe that on this particular model, applying the intervention changes the model from a pro-stereotypical biased model to an anti-stereotypical biased model, which is really good, right? So essentially, the idea is that the takeaway is that while pre-training the models, if you essentially try to use, bias sensitive data, in the sense that somewhere data where bias intervention has been applied, then there's a good likelihood that the overall model that you train is going to be reasonably good. I mean, it is going to have less social bias. The other experiment that they did was to change the training order, while training the LLM. So the question is, does training order influence memorization in LLM? So it could be, very intuitive to think that, hey, if I basically had this LLM model look at some part of the training data in the later part of pre-training, then maybe it remembers it better, right? So to be able to answer this question, or of course, another way of posing this question is, does the location of a particular sequence in the training data set influence the likelihood of it being memorized, right? So remember, while preparing for exams, especially rote learning based exams, you must have seen several students somehow mugging up important things towards the end of the exam. Now, they do that because they feel that, hey, if they try to, remember, they will remember better, right? If they try to remember closer to the exam. So they wanted to do the same experiment with LLMs. The way this was done is to define what is memorization, right? So this is the way memorization was defined, that if you have a string k comma l, it is considered to be memorized if prompting the model with the string of length k, helps the model recover the next l tokens. Right? So helps the model recover the next l tokens as it is. Okay. So they basically, what they did was to basically take for every training sample, they took the first 64 tokens. They prompted the model with the first 32 tokens, and and if the model generates the same next 32 tokens, then you would say that that string is memorized nicely by the model. Okay. Um, and what they observed by doing such experiments is that training order has little impact on memorization. So they basically, of course, did experiments across multiple checkpoints. They also did experiments at different stages in pre-training. And they observed that the training order has hardly any impact on memorization. So memorized sequences are not spaced more densely towards the beginning or the end of the training, and that between each checkpoint, roughly the same number of memorized sequences can be found. Okay. So it basically means that whether whether this model reads the textbook, way before the exam or very close to the exam, nothing much changes. So nothing much changes. So the memorized sequences are sort of, it doesn't favor, data which occurs in the beginning of the pre-training versus towards the end of the pre-training. Okay. The last experiment that they did was to answer this question. Do pre-training term frequencies influence task performance throughout training in LLMs, right? So the another way of posing this question is that if I read a chapter like 10 times, will I be able to answer that question better compared to if I read the chapter only once? Yeah. And, the short answer is that they find yes. The answer is yes. And the way in detail the experiment was done is as follows. You first define term frequency. So you basically say that, hey, term frequency is the frequency in pre-training data seen by each checkpoint. So for example, or the idea is that frequency in the pre-training corpus. So term frequency is defined as frequency of a token in the pre-training corpus as seen by the model up to each chosen training step, right? So essentially, if you're using a checkpoint which was obtained after 13,000 steps, well, you look at the pre-training data for the first 13,000 steps and figure out how many times the particular token appeared in those 13,000 steps, and then you will compute average and then plot stuff based on the averages. Okay, so that's that. Now they did experimentation here using two data sets. One is called as the arithmetic task data set and the other is trivia QA data set. Okay, so let me talk about them one by one in detail as to how they figured out, this correlation between pre-training term frequency versus the performance of the LLM. Okay, so as part of arithmetic task data set, they basically, tried to prompt using this thing. So Q colon, what is X1 hash X2, right? And then A colon. So the idea is that the X1 is a number between 0 to 99 and X2 is a number from 1 to 50 and hash could be plus or times. So it's like an arithmetic task, addition or multiplication task. And the model is expected to, of course, come up with the right answer. Okay. Now, now basically, so we know what performance means. Performance basically means accuracy. The model has to come up with the right answer. And that's basically what is accuracy, right? But then what does term frequency mean here? So the way they define term frequency here is to basically consider the focus on X1. They basically said we'll consider for every sample. So of course, there are many samples which contain X1. So we'll compute the average accuracy across all those samples that contain X1, the number X1, right? And the term frequency for X1 will be computed as as frequency of X1 in the pre-training data until until this checkpoint. Okay, so that's that. Now, they also experimented, by the way, for doing few shot prompting. And in that case, they ensured that in few shot exemplars, they do not use the same digits as in X1, right? So as to avoid the X1 being repeated in the exemplars that are supplied at test time. Okay. So that's that. Now, the other experiment they did was with trivia QA dataset. It's a question answering dataset. So therefore, it is, of course, obvious that the prompt will be of this kind: Q colon question, the actual question, and then a new line, and then answer, A colon, and then the answer. Okay. So, and the accuracy, of course, is exact match accuracy. If the model predicts the answer correctly, you basically, it's a win, right? So that's that. And here the accuracy is computed per example, right? So it's not really, so unlike in the arithmetic task where it was averaged across all examples that contain X1, here you compute the accuracy for every QA pair. Yeah. And therefore the term frequency also that you compute in the pre-training data is basically term frequency of all salient entities of that QA pair. So, they don't define salient entities appropriately, but I assume they would basically mean named entities, right? So essentially you try to see the named in the pre-training corpus, how many times those named entities appear. Okay. So what do they observe? So this is basically the output. So essentially, or rather the results, right? So they've been plotted for 4 different sizes of checkpoints. You observe that, right? And then on the x-axis, what is varied? Well, the frequency is varied. So here, it's accuracy on trivia QA. So I've not shown the result for arithmetic task data set. You can look in the paper, but for trivia QA data set, if you basically, what do you observe? You observe that in general, the accuracy increases with the scale of that model, right? So of course, these accuracies, 12 billion accuracies, are much more than 160 million accuracies. What you also observe is that so therefore small models are worse, right? Small models, you can basically just say that small models rarely produce good results anyway. So forget about being able to see if the frequency of occurrence in pre-training data set matters or not. So small models are bad. But if you look at these large models, what you observe is that as the x-axis increases, the frequency of that particular data point in the, or in this case, salient entities of the QA pair increases. As the frequency increases, you see improved accuracy. So which means that if you have read about that particular entity, a lot, then you would be, then the LLM would be able to come up with the correct answer. Okay. So in other words, model sizes affect the correlation between average performance and the term frequencies, indicating that this correlation is an emergent property. So although you observe that in all of these cases there is an upward trend, what you observe is that the upward trend is really, really good for 2.8 billion or 12 billion parameter models. So model size is basically, large model size basically brings in this nice emergent property. Okay. So in fact, for the multiplication task, for the, one other experiment that they did was basically to look at performance discrepancy between top 10 most frequent input operands and bottom 10% least frequent input operands, right? And they observed that the gap widens over the course of training. So as you have more and more, higher and higher frequency, you observe that the gap in the performance actually widens. Okay. So that was that. And this experiment is very meaningful because, now you could possibly use this knowledge that if something is seen, some answer is seen several times, then the probability that the model will be able to correctly guess that answer is very high. So you can actually infer from the following from this experiment, that one can calculate how many times that information occurs in the training data to predict whether it is likely or less likely that the model of some size will be capable of retaining and recalling this information in a quiz. So, from its training data in a question answering kind of a task. Yeah. So if it has seen some particular data, then it will be able to answer more correctly about it in the question answering task. It was obvious, but it's just that it was never measured. So it was never measured accurately. And Pythia suite enables this kind of measurement to be done. Okay. So in summary, in this video, I talked about the Pythia suite of large language models. Basically, it's a suite of 16 decoder-only autoregressive language models trained on the pile data set before and after deduplication in the same exact order. And the data loaders, by the way, exactly are available for you to download and try out these experiments or other analyses as well on top of them. Specifically in this paper, they actually dealt with 3 different kinds of analyses which deal with the evolution of large language models while pre-training. One is gender debiasing effect. So, and they answer that positively, that yes, if you basically do some interventions before, before you finish off the entire pre-training, then you can actually end up with models which are less gender biased. Right? The second is memorization effects, and the conclusion is that it does not matter which, whether you pretend, where does the sequence lie in the pre-training data, it will be learned in the same way. Right? The third thing is term frequency effects, where basically they found that yes, if something, some sequence was observed lots of times, then the probability of it being correctly answered or it being outputted is higher. Right? So that's basically the analyses that they performed using the Pythia suite. Okay, so that's it for this video. Hope you liked it. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.